Okay. So good evening to all once again. I welcome you all in this lecture, Wave on a String. The other name of this chapter will be Wave Mechanics. You can say it a Wave Mechanics or simply Wave or Sound Wave. Okay. So here we are with our lecture number 4 on Wave on a String. In the previous lecture, we have covered about the equation, how to find out the equation of simple harmonic progressive wave, the velocity of the wave, velocity of particle, acceleration of particle, and we have relate the acceleration of particle, sorry, the velocity of particle with the velocity of wave, okay, with the slope of that curve on the wave. So firstly, give me a thumbs up if the screen is visible to you and I'm audible to you, and make it very quick so that we can start the lecture. Okay, Divyan's respond, Hema. Okay, Pragna has also responded. Got it. So are you guys from JNV Ramnagar? Any student from JNV Ramnagar? Okay, no problem. Because a student of JNV Ramnagar regularly joins the lecture, and that is why I'm asking. So no worries. So in the previous lecture, let me recall some concept. We have derived the equation of simple harmonic progressive wave. In this, first of all, we have discussed about the equation of wave motion. Equation of wave motion mein what we have learned, just a second, it's just a recall part, do not worry about it. What is it? So we can represent a wave as a function of time and position. And why we have to do that, I have already explained it to you. Let me explain it once again. So if you have a wave, and mainly the transverse wave we are talking about, this one, okay, and you want to know here the particle, because in a wave there are multiple particles, number of particles are there which are oscillating. Okay, I'm not saying that they are doing SHM, they are oscillating. Oscillation is the oscillation and SHM is the drop of that oscillation. Okay, so the simplest case of oscillation is SHM. Each and every particle is doing oscillation here. So if I want to know the displacement of this particle, what we have to do? We firstly, I will just say you that try to find out the displacement of this particle. So what will you do? Firstly, you will ask me that where that particle is in the wave, where that particle belong. What is the position of that particle? That is crucial information for you guys. So if the displacement of this particle is yp, let's say this axis represents y, the displacement, this axis represents x. Okay, now this displacement could be anything: electric field, magnetic field, pressure, voltage, this. Okay, so this displacement could be anything. And what is the displacement means? Displacement is the, like we can relate it with pressure. Either we are seeing the pressure wave, we are seeing electromagnetic wave. So electric and magnetic field we have to take as a displacement function. We are seeing the voltage in AC circuit. So voltage we have to put it here. You will see a chapter named AC, alternating current, in your 12th class, and where you have to study this. This same graph will belong to a voltage and time. Okay. So for now, you just have to keep in mind that this y represent the displacement. Okay. Now, what is a wave? Wave is a disturbance which travels from one place to another place. This disturbance could be anything. Either it will be energy or it will be a momentum. Got it? Now, how does a wave form? We have a source particle here at x is equals to 0. This source particle is vibrating. Consider or imagine a string in your mind, a tight string. So you are just start oscillating this end. Okay. So this is the source particle. What happened then? This disturbance which is created by this source particle will travel forward. And this continuation of this disturbance forms a wave. Because each and every particle in wave will do exactly what source particle doing. So here the source particle is oscillating. So that is why this all the particles present in this wave are oscillating. Okay. So if I want to write the displacement function of any particle, what will be the first requirement? The first requirement would be that where is the particle? So here y should be or must be a function of x, the position. If I say you that whatever the particle is present at x is equals to 2 centimeter, try to note down the displacement of that particle. And you have reached there, let's say at x is equals to 2 centimeter. Okay. Now, when you are standing here, you are seeing this particle and just take your notes and trying to note down what is the displacement. And then what you see suddenly that the displacement of this particle is changing with time because it is oscillating. So to measure the displacement, hello student of JNV Ramnagar, how are you? Okay, so displacement of that particle is also oscillating because this particle is in oscillatory motion. It is the displacement of that particular particle is also changing with time. So what we will say that to know the exact displacement, we should know the timings also. So at x is equals to 2 centimeter and the time would be 2 seconds, then you will say, okay, this is the displacement at this particular time and this particular position. So that is why the wave function would be the function of displacement and function of time. More specifically, this function will look like this. Y is equals to f of ax plus minus bt. Okay. Rest I will revise you by this. We have did it in the previous lecture. So this is the wave. So this yellow color ink is visible to you, everyone. I hope it is visible, or let me change it. Yeah. So this is a wave. So when source particle is moving perpendicular to wave motion, that wave is transverse wave. And when it is moving along the wave, that wave is longitudinal wave. So in this particular scenario, this is the transverse wave because the oscillatory motion of particle is like this and wave is moving in this direction. So they are perpendicular to each other. Okay. So this would be the function y is equals to f of ax plus minus bt. Now how to determine that in which direction the wave is going? How to determine that? So there is a trick, or you can say concept also. If both ax and bt have same sign, either plus plus, either minus minus, so that wave is traveling in minus x direction, negative x direction. If the sign is opposite, like ax is positive, bt is negative, or ax is negative, bt is positive, then the wave is traveling through positive x direction. This is simple. Okay. Now, the equation of simple harmonic progressive wave that we have discussed in the previous lecture. So, equation of simple harmonic progressive wave is given by y is equals to x into t, x comma t. function of xt, a sine omega t plus minus kx plus phi. Here you can also see this y is a function of something at or bt plus minus ax. Okay, so that is also satisfying the condition like this, ax plus minus bt. So how many have you covered this derivation? In the yesterday's lecture, I have done it with student of JNV Ramnagar. So I think you have joined. This is a combined class of Pune region and I think Shillong and Hyderabad, because Akshmala ma'am is on leave. So that is why I think. Okay. So how many of you have done this derivation? So I will quickly go through it and explain you. Otherwise, I will do it in a thoroughly way. So please make sure by giving thumbs up. So tell me, how many of you have done this derivation? Okay. So I think the derivation part is done with you guys. Okay. So no problem with that. So finally, we have arrived with this equation. Yp is a sine 2 pi by t, capital T, into small t minus 2 pi by 2 pi x by lambda plus phi. So this is a function of type bt minus ax, is represents a wave. This is a simple harmonic progressive wave because this sine into something represents a harmonic function. So this is a simple harmonic progressive wave. Now this 2 pi by capital T, you can write it as omega. 2 pi by lambda is a quantity which is known as k, small k, which is equals to wave number. So wave number, you just remember for the competitive purpose that what is this k signifies. So k signifies the compactness of the wave. Look, if the k is too large, which means lambda is too low. So if lambda is too low, which means wave is very compact. Okay. It is also termed as wave number. So number of wave is more in that particular range. But if k is less, which means lambda is high, so wave has stretched. So you have less number of wave in this particular volume or in a particular specific area. Okay. So this represents the compactness of wave. Remember it. Compactness of wave. Now, what is phase and phase constant? So this quantity, the argument of this sine function, okay, the argument of this sine function, whatever is written inside the sine is termed as, or any trigonometric ratio, whatever is written inside, it is termed as argument. Okay. So omega t minus kx plus phi is the phase. Phase tells us about the status of wave, where the wave, at what time, and at what specific place the wave is. Got it? Because it involves t, time, it involves x, position, and it also involves this phi. What is this phi? So if you put t is equals to 0 and x is equals to 0, which means we are talking about the source point and the initiation of the wave motion. So it tells us about the initial status of source particle, or you can say the wave. Okay. This is termed as phase constant. Got it? Now, what is particle velocity and acceleration? So we know that this represents the displacement of particle. Y is equals to a sine omega t minus kx plus phi. So if we differentiate it with respect to time, but there is a point here, and which is also crucial. Here I have used this term del by del t. Why? Because here y is not a function of single variable. Here we have two types of variable. First is time, second is x, the displacement in x direction or the position. Got it? So if we are differentiating y with respect to time, that will give us the velocity, because y is the displacement of this particle. So if we see the change of displacement per unit time, it will give the velocity of particle. But we have to differentiate it partially because x is constant for a particular particle. So let's say if you are observing this particle here, so x is fixed for it, na? X is fixed. So if x is fixed, which means we can treat x as constant. So that is why we are partially differentiating it, keeping kx as constant. Got it? So if you differentiate it first time with time, you will have Vp, particle velocity. If you double differentiate it, d2y by dt square, or simply you can say dvp del Vp by del t. It is termed as minus a omega square sine omega t minus kx plus phi. So this a sine omega t minus kx plus phi you can write as y. So it will become minus omega square y. So acceleration of the particle is minus omega square y. Okay. Now, I hope you got it. Any kind of doubt if you have, guys, you can ask me in the chat box. You can put it in the message in the chat box. Now, the speed of traveling wave. Now, what we have discussed earlier, speed of particle, velocity of particle. Got it? And what we are discussing now is the speed of wave. This disturbance that is created by that source particle. What is the speed of that disturbance? That we are going to calculate. So let's say, what is the concept here? Let's say in delta t times, this wave has moved from this position to this position. So each and every particle move with, let's say, delta x position. So this crest, you know that this is known as crest. This is known as trough. So this crest has also moved with the same distance. Now, they are at same position here. Let's say position has been changed, but in a wave, they are at fixed position. They are at crest. So we can say that the phase of the particle has not been changed. Got it? So that concept we have used here, that omega t minus kx plus 5, let's say plus 5, equals to omega t plus delta t minus k into x plus delta x. Got it? Because phase remain constant. We are dealing with the same particle. Firstly, we have considered this 1 and 2. Particle is 1 and 2. Only the position has been shifted. Got it? So that is why the phase is not changing. If let's say we are talking about this particle and this particle here, now the phase has been changed because they are in somehow less positioned. Okay? In the different position there. Got it? So here is also use 5 because initial phase are also same. So they will cancel out 5 and 5. Now if you multiply this omega inside and this k is inside, so you will get omega into delta t equals to minus k into delta x. Now delta x by delta t. Wave has displaced delta x in delta t time. So displacement by time will give the velocity, and take the magnitude of it will give you the speed. So delta x by delta t is the speed of wave, which is equals to omega by k. Now speed I'm talking about is omega by k. If you talk about the velocity, it will be minus omega upon k. Got it? You must have wondering where this minus has been gone, because we are only talking about the speed of wave. That is why we vanish this minus, because speed can't be negative, only velocity can. Okay. Now the another formula that you can use for it, speed of wave omega upon k. Omega you can write 2 pi by capital T, and k is the wave number, remember in the previous slide. So it is 2 pi by lambda. Now 2 pi and 2 pi will cancel out. This lambda goes in the first place. This will multiply with this. So it will be lambda by t, velocity of wave. Now lambda into 1 by t. 1 by t, 1 upon time period gives you the frequency. So lambda into f. So v is equals to f lambda. This is also a formula. This wave speed is of wave. You have studied this formula in your 9th class in the chapter sound. Okay, chapter name sound. In that chapter, this also represents the wave velocity or speed. So v is equals to f lambda. F is the frequency of that wave and lambda is the wavelength of that particular wave. Got it? Now this is the topic that we are going to deal today. Speed of a transverse wave on stressed string. Now, string is a material, we will see, and it is obviously a solid material. Now, the propagation of wave, please focus, because this is very important. The propagation of wave, which means the movement of wave, okay? Propagation of wave in solid. So propagation of wave in solid depends on two factors. First is the inertia property. And second is the material property. Or in material property specifically, you will write elasticity or elastic property of material. Elastic property of material. Now, why is that? Because let's say, for example, this is a string. Rassi, जिसे we can say rassi. So this is the string. And you have tied this string with this end, and another end is in your hand. So you have holded it. And you are oscillating it. In gym also, if any one of you goes in the gym, they have the experience of this rope, skipping rope. Hai na? So let me ask you one thing. If this is a rope and second rope is this, just a second, the rope should be straight. That is why I'm doing this hard work here. Okay, this is another. Okay, so let me ask you one thing. If this rope of 1 kg and this rope is of 10 kg, this is rope A, this is rope B. So which one is easier for you to form a wave? We are forming wave in string. So which one is easier for you? If you want to form a wave, these types of wave. So which one is easier for you? Okay, Divyansh has answered A. Only Divyansh, no one else? JNV Ramnagar has also answered A. Okay, guys, come on. Come on, this is very simple. It's just a logical answer. Hema has also answered. Okay, okay, okay. So what about Jadeja, Yoga, Arya, Stephen? Are you agree with A? Or you guys want to switch the option? A. So everyone, almost everyone is saying A. Now, what is the correct option? Hooray, you got it. So this is A, obviously. Why? Because logically, it is not that heavier than 10 kg. 1 kg is easy to lift. 10 kg is more weightful with respect to 1 kg. So that is why read the first statement written on the slide. Propagation of wave in solid depends on the inertia property, because in any body, this term inertia Inertia is something which resists the change, and more is the mass, more is the resistance. In LNM, Newton laws of motion, we have studied it thoroughly, that more is the mass, more is the inertia, more is the difficult to displace that object, to change, to make any kind of change in that particular object. So that is why the propagation of wave also in solid depends on the initial inertia property. Now, who is that genius who will guess that propagation of wave in solid depends on inertia property? That is right. It is dependent on it directly or inversely, which means propagation of wave means wave speed, simple. It depends on the inertia property in this way or like in this way. Who will guess it? Very quickly. I'm giving you 1 minute. So Divyans is saying B. And firstly, it was saying it is directly. Okay, okay. Got it. Anyone else? I want at least 5 to 6 answer. Yoga is also saying B. Okay, got it. Hema is also saying B. Come on, guys. Jadeja and Stephen. So JNV Ramnagar has only said A. Okay. This. Sorry, I'm not able to pronounce your name. It's Sasri Lekha, I think. And sorry for mispronunciation. You are also saying B. Hmm? Okay. So thank you guys for participation. But the correct option is A. You just have to think a little bit more because you have answered it the previous question that it is easy for us to propagate a wave in 1 kg rather than 10 kg. And I have said you that inertia property directly depend on mass. So which means that more is the inertia, more is the difficult to make wave. So which means if inertia increases, which means mass increases, so velocity will decrease. It is hard for us to propagate a wave in the heavier objects, heavier string. Got it, everyone? So that is why the velocity of wave depends on inertia property inversely. If inertia increases, velocity of wave decreases. Got it? I hope you got it. And this is for everyone who has participated. And so much congratulations to JNV Ramnagar student. They have find it well. Okay. So this is clear to you. Now, the same thing we are going to discuss. Anyone, if any kind of doubt, if you have, you can put it a message in the chat box. You can raise your hand also. Okay. Multiple ways to raise a doubt. Now, if we talk about the elastic property of the material. Okay. Now, why it is important to consider the elastic property? What is the meaning of elasticity? Elasticity is something that to retrieve back, gain back, okay, bounce back. Okay. So elastic property, which means when we applied a force, okay, it got deformed. But when we remove that force, it again regain its shape. That property, the resistance to the deformation, to the change of shape is termed as elasticity. More is the elastic material, more will be difficult to deform it. Okay. Got it? Rubber is elastic. You can stretch it, and when you release it, it will again regain its shape. In wave, what is happening? Some disturbance is traveling. In that disturbance, either it is for, let's say, transverse wave or for longitudinal wave. We will discuss both. This is transverse and simple harmonic, let's say, special case. And this is, let's say, longitudinal. compression and rarefaction. Got it? Now, in each and every scenario of the wave, in transverse and longitudinal also, the particle itself displaced from mean position. Okay, they have got displaced from mean position, but they are again retrieve back this position. They are retrieve back now because it is oscillatory. They are going away from the mean position, being stressed, and then again coming back to the mean position, which means it is also important to consider that how fast, how good they are retrieve back their position. And in solid, the retrieve back position, which means the elastic behavior of the material. Okay, so that is why more is the elasticity, more rapidly the particle will gain its uh, position or retrieve its position. Got it? In air also, we will study the elasticity in gases because they got compressed. So bulk modulus is that factor, change of pressure divided by change of volume or volumetric strain. So in that case also, this air is compressed here, then again it is decompressed or rarefact, again compressed, again rarefact. So they will also depends on the bulk modulus of the air or gas. Okay, so that is why the elastic property of material is also very important, because in wave the particle is displaced from its mean position, and how fast it is retrieved back, it will depends on the inertial properties of, elastic property of material. More is the elastic, more the elastic material is, more will be the frequency of the wave, and more rapidly they will get back to their position. Got it? And you can do it by yourself. You can check it, this concept. You will take the string, a very small string or a wire you can take. Just tied it, both the end. Firstly, tie it in a different way. Okay, not that much tight. And then displace it. You will see a vibration in that way. Then again, tight it very tightly. Okay, do that. Then again, pull back and displace. Then you will see the difference in the vibration. Got it? So more elasticity, because you are playing with the elastic behavior of the of that particular metal, of that particular wire. Got it? So more stress means more tension, and tension is something that is related to elastic property of the material. Got it? So more tension, more will be the frequency of the vibration. So propagation of wave also depends on elastic property of material. Now, if you are talking about the exact derivation, this is not here, but you can get this formula from dimensional analysis, where I'm not going to show you here. I will write the formula directly, that velocity in string, in a stretch string, will depends on C square root of tension divided by mu, where mu is the linear mass density. Okay, mu is the linear mass density, mass per unit length, which represent the inertia property, and tension here represent the elastic property of this particular solid. So this is also verified that velocity of wave will directly proportional to elastic property and inversely proportional to the inertial property. Got it? So this C is 1. The velocity of wave equals to square root of tension per unit linear mass density. So this you have to remember. Okay. Now, this linear mass density is mass per unit length. Got it? So let's say if we consider the string as cylinder in cylindrical shape, the length is L, area of cross section is A, and this string has a mass M. So we can say that mu is equals to mass per unit length. Mass we can write what? Material density into volume divided by length. Now volume of this cylinder is nothing but area into length. So rho into area into length divided by length. So this you can cancel out. So you can replace the linear mass density with the density of material into area. So another formula that you have in your hand is T upon A rho. This is really important for the point of view of competition. Okay. You have directly a formula. You don't have to waste the time. Yeah. Now everyone got it. Then we will move further. If anyone has any kind of doubt, they can ask. Otherwise, we can move on. Now, speed of a longitudinal wave. Longitudinal wave will also developed in sound wave as a sound wave. So what is longitudinal wave first of all? That is the speed of transverse wave. Okay. And here we have a longitudinal wave in which I'm specifying it, in which the particle move along with the wave, or you can say or disturbance. Now disturbance is more elaborative, more specific to the definition of wave. Okay. Now this way also, because longitudinal wave we have seen sound wave. In sound wave we have pressure. Just a second. So in sound wave we have pressure because our ear, how we will able to listen the sound, how we hear the something. It is because our our ear receive the disturbance. And disturbance of what? There are two disturbance we will make through sound. First is the disturbance of pressure, because by compressing and rarefacting, compression rarefaction, by the formation of this, we are changing the pressure of every section in the air. Okay. By compressing it, we are increasing the pressure. In rarefaction, we are decreasing the pressure. So we have a pressure variation also. Also, if you talk about the density, this will also vary, because more compressed is the material, more will be the density. If the material is rarefacted, which means the particles are separated by a large distance, so we have less dense area there. So density is also variable. So we have created two types of disturbance. First is what? First is pressure, second is density. But our air is made in such a way that we are only able to hear the disturbance. This can only read the disturbance of pressure. Okay. This can only read the difference or disturbance of pressure, not the density. Got it? So there will be a change of or disturbance of pressure that will be created by me, and your ear is receiving it, reading it, and then calculating it by your mind, and you will receive what I'm saying. Okay. Now in that case also, this is a wave propagation. So this wave, velocity of wave, we can say in this way. This is for longitudinal. This is also depends on the same way inertial property. Inertial property B here is the bulk modulus and density of the material. Okay. So this is also we can say B upon rho, where B is the bulk modulus. B is the bulk modulus and rho is the density. Okay. Because when sound travels in air, it will change the pressure of each and every section, I have told you. So if it is changing, let's say this is particular volume we can consider. So here, let's say in this area, we have more pressure. And in this area, in this particular zone, we have less pressure. Got it? And what does B represents? You can consider it is a cylinder. So by compressing it, we are changing the volume. So this change of pressure somehow changing the volume by original volume. This is the volumetric strain. So there is a kind of volumetric strain in this particular elemental volume that we have considered. That is why the elastic property here we are considering B. Got it? I hope you got it. Now, and the previous case also, I have just missed one thing, that this is the stretch string. If there is another thing like metal and anything, so you can consider that velocity of wave is gamma upon mu. This is not gamma, it is Y, capital Y. Capital Y here is the Young's modulus of elasticity. Young's modulus. For any specific solid material, you will consider the Young's modulus of elasticity divided by linear mass density, or taking the total mass. If total mass is given, you can consider it. For the stressed string, you will use the only tension upon per unit mass. Now, if you see this, more pressure, less pressure. So we are compressing it and we are decompressing it. So we are changing the volume somehow. So change in volume per unit volume, original volume, will create a volumetric strain. And it has happened because of this change in pressure. So the ratio of this thing will give you the bulk modulus of rigidity. It will. Okay. So there will be a B, Young's modulus, sorry, bulk modulus. Okay. So this is bulk modulus. So that is why in the place of elastic property, I am using this, because this also represents the elasticity of this elemental volume or the imaginary volume that we have considered. Okay. And rho is the density. Density represents mass per unit volume. Mass is the inertial property. Got it? Now, so this is important. Remember it. Now, if we talk about the speed of sound in gases, and this is given by Newton first of all. So what does Newton say? That traveling of wave or slash करके sound in gases You can consider air also, because air is also gas. In gases slash air is a isothermal process. Isothermal process. How? When we are compressing, because in longitudinal wave, sound wave is a longitudinal wave. So in longitudinal wave, compression and rarefaction will form. So when we are compressing it, we are doing work. Okay. We are doing work, which means the heat will be released. Okay. But when this gas expand, it will take up the heat. Okay. Sorry, I've just invert the statement. When we are compressing it, it will gain heat. And when it is decompressing itself, the air decompressing itself, it will take the heat from the compression zone. So that is why the temperature of both the side will remain same. Let me show you by this. If this is a particular volume, here we have compression. Okay. And here we have rarefaction. This is compression. This is rarefaction. So due to compression, there will be a heat produced here. This heat will be utilized by this part of the air in the rarefaction process. So that is why if the temperature is increased, the same temperature will decrease by giving heat to this. So that is why the temperature remain constant. And you have studied the thermodynamics, the process in which the temperature remain constant of the system. What is that process called? That process is called isothermal process. So we consider it isothermal process. Isothermal process. So what is the equation of isothermal process? It is PV is equals to constant. Now if we differentiate it, it will become P dV plus V dP equals to 0. Again, what we will do? We will do that minus P dV is equals to V dP. So dP by dV is equals to and dV upon V. So only minus P will remain here. Okay. Because dP by dV. And then if we consider it 1 by V, again it will go to the first place. Again, you can write it as V dP. V dP. Okay. So this is equation number 1. Now, bulk modulus is also the elastic property. Bulk modulus we can also write change in pressure divided by change in volume by original volume. But when we are changing the pressure, we are increasing the pressure. So volume will decrease. So that is why we have to put a minus sign, because B is a positive quantity. So this B can replace this P in the expression V of wave equals to B upon rho. So in respect of B, we can put pressure upon rho. This is the formula that is derived by this time by me, but originally it was derived by Newton. Okay. So this is Newton formula. Now, if I talk about Laplace correction, Newton has made a mistake there in the previous guide. And that mistake was carried out for 100 years. After 100 years, the Laplace came into the scene, and he has said, he has the courage to say that Newton did it wrong. And what is the wrong thing in the Newton expression? So it's a very simple, minute mistake, silly mistake. Newton can also have that, because this time we will also having it, okay, in the exams. So Newton will also have this silly mistake, although Laplace has corrected it. So what is the fact here? Laplace is also efficient and also logical in this way. Laplace says that Newton sir has considered this process as isothermal. But wait a minute. Isothermal process is a very slow process. But when we talk, this person that is nearby me or at a distance of 10 meter just able to listen to me directly within a second, within fraction of second, which means this process is taking so fast. The time in this process is very less. And also, when we did this, when we take this formula and calculate, when we take this formula, velocity of wave, pressure upon rho, and we take the STP, NTP condition, normal temperature and pressure, and calculate V, it will come out as 280 meter per second. But the actual speed by data is around 332 meter per second. So in this V dash and V, there is approximately 15% error. That is not considerable. Although Newton has a big name, but this we cannot take. This is 15%. Yeah, obviously we cannot afford it. So that is why Laplace came into the scene, and Laplace says that propagation of wave, you can also imagine it what that process could be. Propagation of wave. Tell me in the chat box before I write it. Propagation of wave in, or propagation of sound, I will say. Sound in gas is what? Adiabatic process. Because this process happened so fast, that is why the wave doesn't have any time or the sufficient time to exchange the heat. Okay. So the heat is not exchanging with the surrounding and not is coming from the surrounding. There is no interaction of heat. That process is termed as adiabatic process. Heat input, heat output is constant. That process is adiabatic. So we know that adiabatic process is PV raised to the power gamma is equals to a constant. Again, if we differentiate it, it will become dP. Differentiation of P will dP. V raised to the power gamma will remain as it is. When we differentiate V raised to the power gamma, it will be considered at x raised to the power n. N into x raised to the power n minus 1, which means gamma into V raised to the power gamma minus 1 into dV, and this P will remain as it is. This is a chain rule of differentiation. Now again we have to make dP into V raised to the power gamma equals to minus of gamma V raised to the power gamma minus 1 P dV. What we can say, dP in the previous case also, dP by dV upon V is equals to what? Minus gamma into V raised to the power minus V raised to the power gamma minus 1. So we can write it as V raised to the power gamma upon V into V raised to the power gamma. We have in denominator this one. Okay. This and this will cancel out. So what do we have? We have dP by dV upon V, or you can put this minus in front of this. So it will become gamma upon, sorry, not this V. We will have there. So we have P here. Only P is remaining. So this will become P gamma. And this is also equals to the bulk modulus. So velocity or the speed of wave in gases will be given by B upon rho. Again, you can say this B represents P into gamma upon rho. So this velocity of wave will depends on gamma P upon rho. Only this gamma need to be added. If Newton has added it, we do not have to wait for 100 years. Okay, so this is the actual speed, and by putting the STP and gamma, the adiabatic index of air, we got the correct value 331 or 332 approximately. So this is it by Laplace. This is also termed as Laplace correction. So this is it for today, guys. If you have any kind of doubt, you can ask right now. Otherwise, the lecture is being over. Thank you so much for being attentive. If you have anything in your mind, you can just ask related to this topic. Otherwise, the lecture is being over. Thank you so much. Bye-bye. Take care of yourself. Bye.